Oh, I should turn the mic on. What up, everybody? Welcome to another coffee hour with Paul Abernathy here on a Saturday. It's a little late in the morning, but it is 11 a.m. here in Texas. It is either 10 a.m. somewhere or 9 a.m. somewhere or 12 a.m. somewhere. Who knows? Somewhere. Welcome to the stream. Again, my name is Paul Abernathy. If you're not familiar with who I am, where you been, get on the internet, do a little Google search. On today's coffee hour, I did get a request, and I do take requests, by the way. Somebody asked if I would go over single family dwelling calculations, and could I do it in an hour? And I said, well, knowing me, I'm very long-winded, so I don't know, but I'll give it a shot. So I've got the coffee, and we will get into it. And you are welcome to join me as we go through this exercise, if you will, on single family dwelling calculations. So if you're out there and you're an electrician and you're in the field and you're thinking, I sure wish I actually knew how to calculate the load on a dwelling. I mean, a lot of electricians that I know, okay, no disrespect, will look at it and say, well, that's a 200 amp or that's a 400 amp or whatever, but they probably don't really truly know how it's to be calculated. So we're going to kind of go over that today. We'll do an example, very base calculation, just trying to give you the base foundation of knowledge, and we'll work through that through today's presentation, and hopefully that will help you. Okay. All right. So again, welcome those that are definitely on the stream, and we will get started. I love my Keurig latte machine. Okay. All right. Let's get it on. All right. So, okay. First things first, as with all understandings of a calculation, the first thing starts out with the blueprint or drawing. Now, you might be like doing basements like the Basement King, or you might be doing the entire dwelling or whatnot. You need to at least have a foundation of where things go. So here's my recommendation. If you're an electrician walking into this and they don't have a plan, because sometimes we don't when it comes to residential, and hopefully y'all are all checking out our series that me and Jay do, which is the installation residential wiring overview, where we do a commentary. That's kind of a real helpful. So make you go watch that. That's available over on our YouTube channel. So go check that out. I think we've got up to part 6. There's about 4 or 5 more that we've got to do. But it's really good because it kind of starts giving you that foundation of stuff. But when you're looking at a blueprint, again, if I had a plain Jane print like this or some kind of layout and I'm walking around with the customer, typically I'm going to do a normal layout. I'm going to do my normal 6 and 12s. I'm going to do everything normal. But what I'm going to ask the customer is there anything special you want? Is there a receptacle somewhere where you plan on your layout of your room, your bed, or whatever you're going to do? Now, if this is a spec job and I don't have a customer, it's just being built for the builder, then I'm going to lay it out to code. 6 and 12s, countertops, 2 and 20, 2 and 2 feet from the ends, 2 feet from sinks, 2 feet from breaks in the counter. I'm going to do 4 feet spacing between them. I'm going to do all those type of things, right? The normal. But if I'm doing it with a customer, I want to ask them, what do you have anything special that you need me to have a receptacle outlet at or whatnot like that? And that's what I'll really mark on the plans. Whereas if I'm not going to put everything on the drawing, then I'm going to at least mark with them things that they request. And at the end, that nice big space at the bottom or somewhere on the plans, I get the customer to sign it. This is what we agreed to. But again, if it's just a spec, we're just going to lay it out as normal. Okay, so we're going to do calculations today, but I always like to throw that in there. If you don't have a drawing and you're laying it out, chances are it's just a spec house. So you just follow the code, and the builder, the general contractor, or somebody will tell you if there is something that you need to add. And again, I'm a big believer that when you communicate, you make it noted somewhere. Some of you guys that are just the old school who just say, I don't care, I'll just get in and do it. That's fine, but there will be that time when it comes back to bite you in the butt. I'm just saying. Okay. All right. All right, so the next thing we'll look at here is what is in our dwelling that we're working with. All right, so we have some requirements, some general information that we're going to work with. Again, assuming that the water heater, clothes dryer, counter-mounted cooking units, wall-mounted ovens, electric, everything's going to be electric heat. We're going to assume all of this when it's given to us in kW, that we're going to assume it's equivalent of kVA. Now, we always like to work things down to kVA or even down into the VA if we can help it. But you can still work it in kW. It would still work. Just remember that typically at the end, we're working with a volt ampere value. Okay, so it just makes it easier to work it out. Okay. So here's what we've got on our dimensions, and you need to remember this as we go through it, because we might not jump back to it, but we'll do our best. But here's what we've got. We've got a typical dwelling. In this case, we'll say it's just one level. Although I will remind you that if this happened to be two levels and they were identical, 35 by 55 feet, then you'd have to calculate two levels, right? So you would add both. So if it's 3 VA per square foot, it's per level, okay? Just want to throw that out there. This one, it just says one level. It just shows one level. It's 35 by 55 feet. We're going to need that later, so remember that. And you know what? When you go through these exercises, even this coffee hour, I like to write things down so that I don't have to come back and look at things. That's up to you. But you know, I have it obviously here on the screen, and we'll come back and forth to it from time to time. But sometimes I like to just jot things down. It's 35 by 55. It's got a front porch included within the outside dimensions. So that 35 by 55 includes that porch. So we'll have to do something later with that, as you know. And hopefully you just pause for a second and grabbed your code book, because you'll need that code book. We're working in part 3 of 220, okay? So 35 by 55, we know we got a front porch, which is 7 feet by 10 feet. Now, I'm telling you right now, it's included in that overall dimension, okay? Pretty straightforward. We have small appliance brand circuits. Now, we have 4. That's something significant to remember. So I'm going to write small appliance brand circuit, or the acronym SABC, and I'm going to put 4 beside it, because the National Electrical Code only requires the minimum of 2. But remember, if you install more than 2, and you certainly can, just remember, you have to account for those. It's not like, oh, I can put in 15, but I still only have to calculate for 2. No, 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 no. If I put in 4, I got to account for 4. So remember that, all right? Next, laundry branch circuits. Well, in this dwelling, now we'll tell you, granted, this is only a 35 by 55 foot house. So you're thinking, what, really? But yes, 2 laundry branch circuits are being installed in this house for whatever reason. The code requires a minimum of 1 for these typical small appliance, these typical dwelling units. Keeping in mind that you can always have more than 1. And again, we're not talking about the allowances for multifamily dwellings and if there's a laundry facility on site and all that stuff. We are just doing a single family dwelling today. So again, as I tell people all the time, especially those that prepare for exams, don't let the mind wander. Stick with what we're working with, okay? Then you really can't go wrong if you stick here, okay? All right, this is my point to tell you it is coffee time, so you need some coffee. Okay, we're still awake. Now, water heater. I'm telling you it's a 4.5 kW water heater at 240 volts. I'm telling you we have a dishwasher. It's a 10 amp dishwasher at 120 volts. We have an in-sink waste disposal, which is a lot of fancy words for what we all usually call a garbage disposal or whatever. But again, it only really theoretically not truly a garbage disposer. It's an in-sink waste disposer. There's a certain amount of things you can put in it and things you should not put in it, of course. Now that is given to us in horsepower. So we already know in our mind that we're going to be using this somewhere in a motor aspect of this. So it is going to be one of those things that when we start looking at the largest motor in the dwelling, that's going to come into play, because it is obviously, since it's given to us in horsepower, it's a motor involved. So that's a half horsepower. Now, here's what I like to do right up front, right? This is what I like to do. When I'm going down the list here, I like to go on and start looking at things and converting them. That's just me. You do it how you want to do it. But when I get to the first one, so this is a half horsepower 115. So I'm going to write half horsepower. and it is at 115. Okay, equals. So the first thing I'm going to do, and you get used to doing this yourself because it'll help you later, is I'm going to go to my code book, and I know we're dealing with a motor and we need to find the FLC. So I'm going to go to 430 in my code book. You should do the same thing. And we're going to go on and get this value because we're going to need it later, so might as well knock it out now. And so this is a single phase. It is 115, so we're going to go to 430.248. And we're looking at a half horsepower. We go down to the left, half horsepower. We go to the right, 115. And that's going to tell me that it's 9.8 amps. Okay, so I'm going to write that down. Now, here's a good little tip for you. While you're here, go on and stick a piece of paper on that page because you're going to have to come back in a minute. Okay, so just mark that page. And so it would be 9.8. So I'm going to write that down on my paper, 9.8 amps. And that is the FLC. Okay, full load current. Now remember the nameplate values on a lot of these motors, we say to that as FLA. It doesn't say that in the code, but we say that's full load amps. And the reason we're just trying to distinguish the difference, okay, that's the value on the motor. We typically use that for overloads. And there's some allowances where we would use that for certain things in 430.22. But in reality, what we're trying to find now is the FLC, full load current. And that's why we're going to go to the 430.248 for that. Now, put a mark in there because you're going to have to come back. Okay, so we got that one. We're already here, so let's just do it. The next one we got is dishwasher. So this is a 10 ampere dishwasher. Now, while I'm here, as again, call me crazy, but I need to get a VA value since I'm already here. So I'm going to write this down, 10 amps. And you can do it any way you want, and we'll do it later in our exercise, but I like to get it up front. Just makes it so much easier for me. So I got 10 amps at 120. So I'm going to go to my good old Ohm's law here. Okay. So 10 amps times 120 is going to be 1200. Okay, so we're just going to write, we're just kind of going down the list here, what we need here in our VA. Let's see here. What do we got? Next, we've got trash compactor, 7.5 amperes. So again, I'm going to do the same thing, 7.5 times 20. And that is 900. So that 7.5 amps is going to equal 900 VA. I'm just writing it down for later. Okay, you don't have to. You can do it as we go because we are going to cover this again. It's just a habit I have. The next one is 12.6. That's the 3 attic fans at 4.2 amps each. So there's 3 of them at 12.6 amperes each. Cumulative, the total VA contribution would be 12.6 times 120. Okay, so that is the 3 fans. Total is 1,512 VA. Just doing it ahead of time. Next, when I get down to the clothes dryer, 5.5 kW, we know it's synonymous with kVA, and I like working in VA. So we know this is K being 1,000, so this is 5,500 VA. We already know that. We don't need to write that down. Counter-mounted 7 kW, again, equivalent to 7,000 VA or 7 kVA. We got to work that later. Wall-mounted oven, 6 kW. Again, the same would be at 6 kVA or 6,000 VA. All right, electric heat. Now, in this case, we're going to determine this is not a heat pump. This is separate heat that it is going to utilize an AC handler's blower as well to blow that heat. So it's a separate heat, okay, in our exercise. So it's 15 kW, that's 15,000 watts, that's 15,000 volt amperes, right? Let's see here. The next would be the air handle motor. So here, since we don't have horsepower on these, although we know that these are motors here, and this air conditioning compressor is treated as a motor, and then we have a condenser fan motor, we can go on and solve for the VA right now, and we'll verify that later. So let's just go on and write these down. It's an exercise you can get used to doing. So 3.2 times 115. Yes, use what's given in the question. So it looks like that air handler is 368 VA. Okay. And then we got the air conditioner. the air conditioning compressor outdoor unit. That is 16.6 times 230. So the AC is 3,818. And then lastly, the condenser fan motor, 2 amperes. So 2 times 115 is 230. So that's 230 VA. Now, why did I do this first? Because I always teach these in different ways. We're going to go lesson by lesson. But here I teach you up front how we take an ampere rating and a voltage and convert it to VA. And we're going to need that in our overall calculation. So I also show you a little step of how we go and find the motor. In this case, the FLC for that in-sink waste disposal, because it gives us it in horsepower. And we also, once we get the amps, then we can do the exact same thing and convert that to volt amperes. Okay, and work through it so that we got our numbers. Although we're going to cover that, I just want to push you through the numbers first. All right, so let's kind of get into this. All right, what do I do first? All right, so we went through all that exercise. Now, I'll remind you, you didn't have to do all that. We're going to do it again. But again, it's just some of an exercise I'm used to doing with people. All right, so the first thing we're going to do in the code is look at 220.14J. This is where we're going to get the rules, and it used to be in the 2017 code. 3 VA per square foot was in 220.12, the table. If you're in the 2020 code now, you'll notice it is not in the table anymore. All right, so let's go on and be very active, folks, this Saturday morning. Okay, have some coffee, shake the cobwebs out. Long night playing Call of Duty for some people. For others, just, if you look at J, in the 2020 edition, you'll see a lot of grayed out text. Well, that's because these are, in addition, these are new stuff that was added or moved or reorganized for the 2020. So if you look at it, the very first paragraph you've got tells you that it's 3 VA per square foot. Okay, and we're doing a one family, so this applies to us. So the load for this residence is 3 VA per square foot. The floor plan, if you remember earlier, was 35 by 55. Now remember, it said that front porch was included in that overall dimension. But if you look at that code, and I'll remind you to look at that. Now, where do you look in the code? Now, what you want to look at is 220.11. That is also new for the 2020. Now, not new in a sense that it's totally new information. It used to be in 220.12, and now it has its own section in 220.11. And if you look at it, here's what it says. The floor area of each floor shall be calculated from the outside dimensions of the building. Well, we've got that, 35 by 55. It said dwelling units and other areas involved. It says for dwelling units, the calculated floor area shall not include open porches, garages, and unused or unfinished spaces not adaptable for future use. Well, in this case, we have a front porch. It's included, and it is basically an open porch. And so we are not going to include that in our calculation. And of course, as it says right here on the screen. But we got to take that away. We got to reduce that. Well, the first thing is we need to get our overall. So 35 by 55, never trust my math. You do it yourself. That's a whole part of learning. So 35 times 55 is 1,925. Now we're going to go on and take away that dimension, which is 7 by 10. Okay, so 7 by 10 is 70 square feet. So I'm going to take 70 square feet from that. So that gives me 1,855, right? Now we're going to take that and we're going to do that at 3 VA per square foot. So times 3, that is 5,565. Now, as I always say, this is something you want to write down, okay? Because this is your very first part of your calculation that we're working up. This is your actual 3 VA per square foot and how you came up with it. Now, at this point, it is a reminder that if there was a second floor, then that would be included in here, okay? So again, the 3 VA per square foot is based on your square foot floor area. And in this case, we just told you it's just one floor or just one dimension. But always remember that. You have to account for that, okay? Also, if you have a basement that is unfinished, remember, that is adaptable for future use. So you have to count that square footage in your 3 VA per square foot. And the good thing about that is that when people come back later to finish off that basement, let's say the basement king out in Colorado, he does not have to reinvent the wheel because that basement's general lighting and general use receptacle has already been figured into the 3 VA per square foot. So he doesn't have to do any more. Now remember, he knows, as you should know, that if you add something different down there that's not part of the general lighting or the general use receptacles, then you do have to account for that load. And so then you're going to have to do a calculation to determine whether or not that surface is still adequate for that. And more than likely it probably is, but you wouldn't know that unless you did a calculation, of course, right? All right, so far so good. So we know what our value is, so make sure you write that down. That's our first thing. All right, now we get to come back and we can mark that off the list. The next thing we got on this list is the small appliance branch circuits, and we're going to tackle that next. And so we're just kind of going down the line. Oh, here we go. So the small appliance branch circuits must be calculated as in 220.52a. So if you've got your code books, go to 220.52a. And here's what it says. It says in each dwelling unit, the load shall be calculated at 1500 volt amperes for each 2-wire small appliance branch circuit as covered in 210.11c1. Okay. Now, what this tells me is that 210.11c1 says you have to have a minimum of 2. But we're installing 4. So this tells me that I'm going to have to take a 1500 VA for each one of them. So our house has 4. Now, how would this happen? Well, that's not a very big house we have here, but let's say they put the 2 small appliance branch circuits for the kitchen. And let's say they add another small appliance branch circuit to pick up the dining room and maybe the nook area. Then that is another small appliance branch circuit. And maybe they run another one to pick up a pantry. I'm not sure why you would, but if you did, then that's another small appliance branch circuit. Why? Because the small appliance branch circuits are all detailed in what you're required in your calculation. Okay, so at the end of the day, you're adding them in, that's what you're going to be running into. So make sure you're aware of that. Next, it says in our single family, obviously we have 4, so we're going to be 1500 each. And a note, these loads are going to be included. Can be included in the general lighting load, and when it comes to being subject to some demand factors that we're going to do later. Okay, so remember, we're going to apply a nice little demand to all this, but right now we're just calculating it out, putting it in there. So we've got 4 of them, obviously 1500 each. That's 6,000 VA. So we're going to write that down on our little list right down. So I've already got the first one. That's the general lighting and general use. Next one I'm writing down is small appliance branch circuits, right? I know you got that written down. All right, so let's move on to that laundry. Well, if you remember in ours, the laundry, it says that it has 2. Now, of course, you have to have at least 1 in this one family dwelling that we're calculating as per 210.11c2. And we're putting 2 in. Now, where do I get the VA value? 220.52b. And if you look at it, it'll tell you for the laundry, what's the value? And again, 1500 VA shall be included for each. Now, even though the code says you only need 1, notice that it's very specific here. It says for each. So we have 2. So it's 1500 VA each, right? So laundry circuits, 2, 1500 VA, that's 3,000. So there you go. There's 3,000. And I should remind you that it is coffee time. Yes, there is coffee in here, just so you know. And I just spilled some. All right, it is getting cold though. All right, so we're adding this all in. So our next step is 1500 times 2. That's 3,000. Write that down on your list. All right, next. Okay, so we covered all of those aspects of the general lighting, general use receptacles. We've covered the small appliance. We've covered the laundry. All of those now are subject to a demand factor that we can apply. All right. Now, before we can apply a demand factor, we need to know what it says about applying and how they're applied. So if you look at part 3 of Article 220, it deals with the standard method. Of course, that's what we're doing today. On another coffee talk in the future, I will do the optional method. But right now, the reason I'm doing the standard, and I know most people will say, Paul, I don't use the standard method. I always use the optional method. This is for all of my folks out there that are preparing for an exam. Chances are you need to know how to do the standard method. Plus, even if you're doing the optional method, you're ultimately going to have to do both anyway. You know why? The neutral. The neutral can only be calculated by the standard method, not by the optional method. And the reason for that is that the neutral conductor calculations and all falls under part 3. It doesn't fall under part 4 for the calculations. Of course, part 4 is optional. Part 3 is the standard method, right? So that's, until that's changed, that's how it's got to be. All right. Now, let's keep on getting it. Oh, also note that it may say general lighting, but it also includes the general use receptacles as detailed in 220.14J as well. So before we even go and start doing the calculation, let's kind of give you another quick look at 220.14J real quick. If you look at here, I want you to see what it says. Now, what we did was the 3 VA per square foot. That's what we got from it. And also, if you look down, you'll see number 1, number 2, number 3. Let's look at those real quick. For those that have the code book, it says all general use receptacles under receptacles of 20 amperes rating or less. So that's going to cover 20 amperes and 15 amperes. Including receptacles connected to the circuits in 210.11C3 and 210.11C4. So that's the bathrooms, and that is the garage if you have a garage. So that means that I don't have to add any VA for those. They're already covered. They're already in there. So I don't have to do anything special for that. I don't have to add any additional VA for that. Now, we still have to have those branch circuits. But as far as the VA is concerned, it's already covered in that 3 VA per square foot. So that's a lot of people get confused on that and say, well, do I have to add 1,500 for the bathroom? No. Do I have to have 1,500 for the garage? No. Already covered in those 3 VA per square foot. And that tells you that right here in 220.14J1. Next, it says 2, the receptacle outlets specified in 210.52E and G. So if you go back and look at 210.52 E and G, what is that telling you? Well, 210.52, let's go back and E. Okay, that's your outdoor outlets, right? For those applications. So that's already covered. That is the receptacle, let's say, for one family dwelling at the front and one at the back of the dwelling. It's already covered. In this C and G is the receptacles in your garage. Now, granted, we have to have the circuit in there to cover the receptacles that are not over 5.5 feet, and they're dedicated for each vehicle bay. Okay, so for example, if you have 3 vehicle bays, you got to have a receptacle for each bay. Still, it's the same 20 amp branch circuit, but you have to have a physical receptacle outlet positioned for each vehicle bay. We already got that covered, right? Already got that covered. I don't have to add any value for that. I don't have to add any VA for that. It's already covered. It tells you right here that it's already covered. So. And of course, then the last one was lighting outlets is specified in 210.70. That's all of the lighting outlets that you're required in your dwelling. The ones that are covered in 210.70, those that meet that rule are covered in the 3 VA per square foot. Okay. Again, we're talking one family dwelling. All right. So that's where we got that from. So I just wanted to make sure everybody was okay with that. All right. Let's keep on getting it and see how we apply these rules that's in 220.42. All right, so when you got your code book, I'm going to go to 220.42. Now, that's a pretty important table, right? Because it's telling me, first of all, let's read the code rule before we even look at the table. Let's read the rule. It says in 220.42, it says the demand factor specified in table 220.42, which is what we're going to look at, which for the dwellings is right there on the screen. It says table 220.42 shall apply to that portion of the total branch circuit load calculating for general illumination. They shall not be applied in determining the number of branch circuits for general illumination. Okay, so we're just doing this to calculate the load. Okay, we're doing a load calculation here. And so in this case, remember that 3 VA, it tells us, although it states it's for general lighting, it is also covering the general use receptacle loads, right? So that's all covered in here. So just making you aware that everything is covered within that. So now we're going to look at the table. And I've got it on the screen so that you don't have to go to the code book if you want to stick right here, right? So dwelling units, the first 3,000, 100%. So I use that old technique. I just take the 3,000 and put it aside. That's the technique I use because I'm going to add it at the end. You do whatever you feel comfortable with. The next value is 3,001 through 120, or you'll hear us say in the industry, Once you get past the first 3,000, we'll say the next 117, because 117 plus 3,000 is 120. So that's just, you might hear somebody say it that way, but that's really what we're saying. So the first 3,100, the next 3,001 up to 120,000, then that is at 35%. And then any of the values that are over 120, then we're going to take that at 25%. Pretty straightforward. Although I will tell you, if we're a dwelling unit, single family dwelling, that would be massive. Okay, that would be like maybe the basement king's house or something like that, because he lives in luxury. I'm just saying, the lap of luxury up in Colorado. Just saying. All right, so if we did that, all right, so we took our values that we did from the first 3 steps right here, and we're going to add those up. Again, don't trust my math. Grab that calculator. I know it's early here in Saturday morning. You worked all week, and you're thinking, dude, Paul, I don't want to do calcs. But yeah, you do. Deep down inside, you do. You know you do, right? You live for this. All right, so we'll turn it on. So I'm going to do 5,565 plus 6,000 plus 3,000. And that is 14,565. So the number is correct. Now, the first 3,000 at 100, take that aside. So as you see in my math, I'll take the first 3,000 and subtract it away, put it aside. So that gives me 11,565. Now, that does not exceed the 120, okay? So we're going to be at the next one, which is anything over 3,000 up to 120, over 3,000 up to 120, we're going to use 35%. Good. So we take that 11,565 and we multiply that by 35%. You know how I like to convert everything down into decimal. It's the way it should be worked. So I start from the right, move 2 spaces to the left, and it ends up being 0.35. So work this out. It's 4,047.75. Of course, this 0.5 and higher, I'm going to round it because the code says I can. Okay. Now, if you ask where does the code say you can, then go back and look at 220.5B. And if you look at 220.5B, it says fractions of an ampere. It says calculations shall be permitted to be rounded to the nearest whole ampere with decimal fractions smaller than 0.5 being dropped. So this is 0.7, so I'm rounding. So that's why I round. So we've got 4,048 VA. Now, we got to add that original 3. Remember, we kind of tucked it away. We put it to the side. We had to take that at 100%. Okay. So we add it back in there. So that takes us to 7,000. And well, since we already rounded to 4,048, here we're just adding the whole numbers together, but we're going to round it. So it should be 7,048 total. Okay. So that is the 4,048 plus the 3,000. Okay. So you write that down. Guess what? You're done your first overall step in your calculation where you have added the demand factors for the general lighting and general use, right? Now that's huge, isn't it? What did we go from? We went from, what was it? 14,000 and we dropped over half of that off. We're down at 7,000, okay? Right, so the demand factors are huge. Okay, so we dropped that down to 7. So write that down. Let's keep getting it. All right, back to our question. So now we've knocked off the first 1, 2, 3, 4. Now we're getting down to the appliances. We are knocked off all of it. So if you're an exam and you're taking an exam and they want to know the general lighting and they want to know what the calculated load is versus what the connected load is or what the demand factors applied, then remember, if it's just a connected load, you take full values. If it's the calculated load, that assumes that you're going to have to apply something. And so like if you were doing an exam and they wanted to know after demands, what's the calculated load, and it tells you it's a small family dwelling, guess what? They got to give you the dimensions. They're going to have to tell you how many small appliances in there if they expect you to do more than 2, because 2 is the minimum. And then you know you have to have at least 1 laundry. But if they give you more, remember, you got to add the VA for more when it comes to small appliance and laundry. So just things to think about. Stop, take a breath. Exams, folks that are taking an exam, they're trying to test you. And in the real world, you got this. But on an exam, you don't know what they're going to throw at you. So just be prepared. All right. So let's talk about these appliances now. We're moving it. We're clicking. Step, step, step. We're moving on. Now, we're talking about all these appliances. The term appliance designates utilization equipment commonly built in standard types. garbage disposers, dishwashers, ranges, all those type of things are typically appliances. But what I want to point out is you're not going to, in this calculation, you're not going to use things like ranges, cooking units. That's going to be handled separately, okay? But you are going to count things like your water heaters, garbage disposals, dishwashers, things like that. Those are all going to be in here, okay? Now let's kind of break this thing down. For the purpose of these calculations, again, remember that kW is equivalent to kVA. Keep it simple. How horsepower ratings must be converted to volt amperes. Now, you remember something we did earlier? We did that already. So we kind of saved ourselves a step, but you didn't have to. You could do it now if you want. Also remember that any motors that are given in HP value, that we're going to have to go to look at 430.248, because that is single phase. And if we're doing a dwelling unit, we're doing single phase. So we have to find the FLC first. And in our equation, the only one that we did, if you remember back, if you're coming in late, if you remember, the only one that we did was the in-sync waste disposal, because that's the only one that gave us a horsepower, and that was a half horsepower. So we did that. All right. So let's see. No derating allowed when there's only 1, 2, or 3 fastened in place appliances. So again, if there's 3, 2, or 1, you're taking them at full value. You don't get to apply any demands here. Okay. You still got to count for them, but you just don't get to apply any demands. Now, 4 or more, guess what? 4 or more fastened in place, we're going to get to take some demands here. All right, so for service and feeders being calculated, it contains 4 or more fastened in place appliances. The combined volt ampere rating of those appliances can be multiplied by 75%, which is the demand factor. Right? Now, here's a little tip. Again, multiplying voltage by the amperes produces the VA. And remember, we need VA when we're doing these calculations. So here's what we had in our example. We had a dishwasher. We had a water heater. We had waste disposal. We had the trash compactor. Do they even make those anymore? I guess they do. And we have 3 attic fans that we're going to consider into this, okay? Now, when working with appliances, I like to get the VA. We've already done that, but again, a rehash again what we did earlier. How do we do that for the water heater? Well, we know 4,500 kW equates to 4,500 VA, so we got that one. Dishwasher, we already did it. 10 amps times 120 is 1,200 VA. We already did that. In-sync waste disposal, we had to go hunt for that FLC. When we found it, that was 9.8 amps, and we do that times 115 because that's the value that they gave us. And so that is 1,127. That trash compactor is 7.5 amps times 120 volts. That's 900. We already did that. And of course, we did the 3 attic fans at 12.6 amperes times 120. So that is 1,512 VA. So we already did these earlier. Saved you a step, if you will, by knocking it out right away and converting all that stuff. And me, I do that automatically, especially if you're on an exam where they give you a scenario and then you know there's going to be a bunch of questions later about that scenario. And some states do that. They'll give you a question and they'll build questions on that example. Well, that's why I like to just knock out and do all the math up front, convert everything, get to my VAs. It just helps me later, okay? Because I know I've got a bunch of questions based on that. So I've done it all. So let's add it up. 4,500, 1,200, 1,127, 900, and 1,512, 1,512, whatever. So there you go. That's all of these. So we have 9,239 VA. Don't trust me. Never trust but verify. You know, people say Paul can't count. So, you know, let's do it. Or maybe you don't have me in your considered a trusted source yet. Maybe you don't think I know what I'm talking about. That's okay too. You know, got my trolls out there. It's all good. So that's 9,239. That's the VA we've got. Now, I can apply. And who says I can apply that? Well, the code says I can apply that. Where do we go? Where do we go for that? 220.53. So you got your code book? Go look at 220.53. What does it say? It shall be permissible to apply demand factors of 75% to the nameplate rating load of 4 or more appliances rated a quarter horsepower or greater or 500 watts or greater that are fastened in place. Okay. Now, what I'm going to tell you here is that it says you're permitted to do it. So I shudder to say this, but in the real world, if you don't want to apply the 75% demand factor, you don't have to. And with that, I need some coffee, because that means people are just not taking advantage of the code. So I'm going to have coffee, because that makes my head hurt when I think you don't take advantage of the code. So, God, that's good. All right. It's not Starbucks, but I'm boycotting Starbucks. Okay. So there we go. So we take that 9,239 VA times 75%, and don't, again, verify me, times 0.75 is 6,929.25. I'm going to drop that 0.25 because why? 220.5B says I could, so I am, so I is. So that is going to be 6,929. So that is my appliance contribution. Write that down. Next, let's tackle that clothes dryer. Remember, we're going down the list. We're boom, 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 banging them out. So now the clothes dryer is not a requirement for load calc. In other words, if you're on an exam and they don't tell you that there's a clothes dryer, then you don't have to guess at one. Say, oh, I got to add 5,000 for a clothes dryer. Absolutely not. Only if they give it to you that you take it into consideration. In the real world, if you're putting in a dryer and you know you're putting in a dryer, 30 amp receptacle outlet for it to put a device in it, then you got to count for it. Okay, common sense? Yeah. All right. So in this case, ours includes a clothes dryer. So what do we got to go look in the code? We got to go look at 220.54. So we should be already here. What does it say? 220.54 says the load for household electric clothes dryers in a dwelling unit shall be either 5,000 watts, and you notice it has VA in parentheses. Again, to remind you that they're synonymous. Okay, in calculations, we can utilize VA, and then we always like to get to VA ultimately. So it says, or the nameplate rating, whichever is larger for each dryer served. Now, we don't have to go to the table for this, because the table says 1 to 4, you got to take them at 100% anyway, right? So we're not doing a calculation. We're going to have 5 clothes dryers in that type of scenario where we can even go to this table for some demand factors. We really don't. The key for you to remember here that it has to be at least 5,000 or the nameplate, whichever is greater when you're doing the standard method. Well, 5.5 kW or 5,500 VA is greater than 5,000. So that's what we have to take because of what the code tells us. Okay, so a clothes dryer, neutral. We'll also remember that at this point, it's always a neat thing to do is, since you know you're going to have to be doing a neutral load at some point, why not do it now while you're here? So take that 5,500, all right, and multiply that by 70% and write it down. Save you a step later. So I'm going to do 5,500 times 0.70, and that is 3,850 VA. Just lock that in your brain or write that on the paper and put it in beside it for the dryer's neutral contribution, because you're going to add that later. But just want to remind you, you're already here. Might as well write it down. Save you a step. All right, next. All right, so 5.5 kW is equal to 5,500 watts, which is synonymous with 5,500 VA. And I want to mention, for those that think we aren't live, we are live. Thank you, Swartzy, Adam, Walter, for joining me over on the actual stream. We appreciate you for tuning in here. It's a little late maybe in some places for coffee, but you know what? It's coffee hour somewhere, so I'm going to enjoy it. Maybe in China, it's coffee hour. Maybe, no, I don't know. It's midnight there. I don't know what it is. All right, anyway, enjoy the coffee anytime during the day. All right, so that's our contribution for dryers, 5,500 VA. Write that down. Jot it on your sheet. Move on. Now we're going to get to the cooking. Household cooking appliances are not required in a load calculation. Did you know that? If you have cooking, you account for it. If you don't have cooking, you don't account for it. Although I don't know any single family dwelling, and I don't know of any calculation anywhere, whether it's for an exam, that would not have cooking, a range of something. So in this case, we got an oven and a separate cooktop. okay, together can be treated like a range, single range, but we have to account for it. Why? Because our calculation accounts for it. Now, here's an interesting thing. People say, well, what if my cooking appliance is less than 1 3/4 kW? Do I just get rid of it? The answer to that is no. You just don't get to apply any demands to it. You still got to account for its load. So you just add it in there as the load. Right now, what we're trying to do is to see, do I get any breaks on this thing? Do I get any reduction on these things? That's what I'm looking for. And in our case, both of our cooking appliances are well over, okay, 1,750 watts, okay? Or again, 1 3/4 kW, okay? Or 1,750 VA. You get me? It's all the same. All right. So since it is, we got to do it. Absolutely, Schwartzy. It's never too late for coffee. All right. So individual appliances rated more than 1,750 watts or VA can be derated by using table 220.55 demand factors and all of the applicable notes that are under that table. That's another interesting fact that some people don't know. We're so used to hearing things like informational notes. Notes are not informational notes, folks. Y'all know that. My fast tracks folks know that. So, but notes are very much part of the code rule. So if you see something in a code that has note, then it's applicable. You got to apply it if it's applicable to the question or the calculation you're doing. If you see informational note, it's not requirement. Hey, it's good information. In fact, I'm a big fan of informational notes. Okay? So it's kind of, and again, but that's the educator in me. Code purists that are on code panels, most of them hate informational notes. I love informational notes because, again, I know that the NEC is not a teaching document. It's not designed for the untrained, okay? It's not an installation manual. It says all that right up in the front. But I'm still an educator. I still think that we can teach with the NEC. And how many classes have you gone to that they're actually teaching using the NEC? So we can say what it's not, but you and I know what we use it for, right? Not just an installation, but we use it to teach. So an informational note helps give guidance, okay? Okay, and I know I'll get those upset, those purists out there. They don't have to watch. Turn the channel, change the channel, unsubscribe, bye-bye. All right, so while we're here, remember, also, when we do this, we got to do a neutral calculation. And 220.61b also again tells us that we can take the values of whatever we're going to come up with at 70%, right? So while you're here, you can always jot that down so that you don't have to do it later. But we will. Don't worry about it. And I'm just going to tell you up front that coffee hour is probably going to go over because for some reason on this Saturday morning, I'm very yippy. So I'm just chip, 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 chip. So something may be in my coffee. I don't know. All right, so what do we got here? We've got a 7 kW cooktop, and we got a 6 kW wall-mounted oven. All right, so a 7 kW counter-mounted cooking unit and a 6 kW wall-mounted oven are included in this calculation. Both fall within what? So let's go to table 220.55. So if you're looking at this big table, and you're seeing something here, and I'll read you the heading of this table because this is important. It says, demand factors for loads for household electric ranges, wall-mounted ovens, counter-mounted cooking units, and other household cooking appliances that are over 1 3/4 kW rating. And then you got the parentheses here. It says, column C, to be used in all cases, except as otherwise permitted in note 3. So if note 3 doesn't apply to your situation, then you always use column C. Simple, right? When they say it like that, it's pretty straightforward, right? Okay, so at the end of the day, we need to see if note 3 is going to apply to me and you in our example of this house we're wiring. So if I look at note 3 and it says, okay, they're over 1 3/4 through 8 3/4, and ours are, one is a 7 and one is a 6, boom. Note 3 is applicable to us. It says, in lieu of the method provided in column C, so again, instead of going straight to C, it says, it shall be permissible to add the nameplate ratings of all household cooking appliances rated more than 1 3/4, but not more than 8 3/4, okay, and multiply the sum by the demand factor specified in column A or column B for the given number of appliances. Wow. That's powerful there. It says where the rating of cooking appliances falls under both column A and B, when ours does not, by the way. It just falls under B, if you will. But if it did fall under A and B, it says the demand factors for each column shall be applied to the appliances for that column and the results added together. Okay? So you could do that, and you could add the results, could be added together. Okay? So in our case, it's all B. So we're easy peasy, lemon squeezy. So what we're going to do here, also want to give a shout out to James popping in on us. Thank you for joining. And again, Adam, I'm glad you always learn something from my classes. A lot of people say I don't do as many anymore because now I've sold out and everything's subscription on my website. So all of my YouTube haters out there say, you don't give the free education anymore. What am I doing today? I'm giving free educations. So I tell all those people out there, stop whining. I do my best. Have some coffee. It's Saturday. We're not working. We're working the brain, but we're not working the physical. Okay. All right. So anyway, back to where I was. All right. So in this case, they're all in B, and I'm going to do B in lieu of C. Now remember, I still have to compare to C because I'm doing something in lieu of C. All right. So let's see whichever one comes up with the lowest value I can use. Okay. All right. So let's see what we got here. So we're under B. How many appliances do we have? 2. So we go down to 2. We go to the right. 65%. So what am I going to do here? I'm going to take it and add these two together. 7 plus 6 is 13. I'm going to multiply that by the 65% because it says I can. All right. And that is going to be what? Let's do it. Get your calc. 13 times 0.65. And that is what? 8.45 or 8,450 VA or 8.545 kW. However you do it, but you know how I like it, right? You know I like to get it down to VA because ultimately that's what we're going to use when we take the total VA and divide it by our voltage to come up with our amps. So we're sizing services. So you know why I'm going there. Just get used to doing that. All right. So again, 8.4 kW equates to 8,450 watts, which is synonymous with VA. So that's 8,450 VA. Now, I want to compare this to C. Now, if you look at C, it's 11 for 2 appliances. The demand value, the kW would be 11. Well, I'm going with the 8,450. It's less. Code allows me to go with that. So I'm going with the less. Okay, so write that down. Okay, that's our next value that we're going to carry on. Now let's move on. We've done the heat. I mean, we've done the cooking. We've done the appliances. We've done the general use and general lighting and general use receptacles. We've added the small appliances. If you came in late, shame on you. And we already done that, but we'll give you a summary in a minute. So now let's hammer out these loads. Now I've heard you folks out there say, Paul, explain the difference in what's called non-coincident loads. Now, you've heard me explain this ad nausea before if you're in my fast tracks, but let me kind of give you maybe a 30,000 foot view because it doesn't just apply to residents. It can apply anywhere. So 220.60 is a broad application. If I have an industrial building or a commercial building and I have 2 different loads and they're designed to not come on at the same time, and there's a way to keep them from operating at the same time, they won't be energized simultaneously, then those are considered non-coincident loads. And I just take the larger of the 2. And obviously, if I size for the larger one, when the one that's the lesser size is running, it's obviously nowhere near the larger one, so there's no problem. That's why we look at the non-coincident load and we take the larger, as long as they're designed not to come on or operate at the same time. That's the whole concept. So that's your 30,000 foot view of a non-coincident load. When it comes to a dwelling, what in a dwelling is potentially non-coincident loads? Well, because of thermostat control, and again, that's why you got to be careful, because if you have a heat pump, then they're not non-coincident loads, because you could have a heat pump where the heat strips also come on maybe to defrost mode or something like that. So if that's the case, they're not truly non-coincident loads. So you got to go and follow the application, and it gives you guidance in here for how to address that. But if you do have non-coincident loads, and in our example, we're going to say we have non-coincident loads because of the thermostatic control, the actual physical electric heat, maybe it's heating coil box that's installed in the HVAC system, that is controlled separately. Okay, when that is on, the air conditioning, compressor, and everything is not. Okay, so they're non-coincident loads. Okay, so that's why I use the term may. Okay, very important. Okay, so that's very important to do that. Yep, James, it will be live on there after I'm finished, so people can watch it later as well. For those that who missed it, can obviously come back and watch it. All right, so let's do this. We got to work our math here. Now, remember what we did earlier? We basically saved ourselves some time, although I am typically a ratchet jaw, so I keep going over things multiple times because it's a method of teaching that I use, whereas I use repetition. Some people say, Paul, you go over things over and over again, and then they want to put something nasty. It's because you're not an educator. You might be somebody on one of those forums, one of those well-known forums that think you know what you're talking about. Maybe one of those really well-known forums where you're the expert. Yeah, you've never taught before. Repetition is a method of teaching. It instills retention. You might want to try it sometime. All right, so in this case right here, the air handler. We're going to do each one of them. The heat's easy. We'll save that for a second. So let's do that. So the air handler is 3.2 amperes. 115 volts. Remember what we're going to do? We're going to take our amps times our volts. That's going to give us a VA. So in this case, it would be 368 VA. That was 3.2 times 115 volts. That's 3.68 VA, right? Now, since both the loads are energized simultaneously, what that means is when the heat is going, our air handler will blow that heat. So that means that blower is going to be going whether it's heat or whether it's AC. So that is a load that we always have to add in to our heat and in our air conditioning calculation. Okay, so we're not talking about a heat pump here. Okay, so in this case right here, since it will run for both, in our case, the very first one was 15 kW for the heat. So as you can see right here, if we were to take that 15 kW and we add that 368 to it, so it's 15,368. So that's our heat. And that is including the air handler because that will run simultaneously. The blower motor will run regardless of whether heat or AC is on. So we have to account for that. Remember, we're trying to establish the comparative between the two. Next, it's fixed heat and the loads are calculated at 100% per 220.51. So that's why we took it at 15 kW or 15,000 VA, volt amperes. Now, since that air handler will blow for the AC, now we got to do the AC. So here's the AC. We'll start with the compressor right here, 16.6. Now, you remember we did this earlier. 16.6 times 230, that's the number it gives us, so that's what we use. That's 3,818 VA, okay? So the condenser fan is 2 amps, that's this one. So that's 2 times 115. We did this earlier. That was 230 VA. And then lastly, the air handler again, because again, it will blow that cold air. So that is 368. You add all that up, it should be 4,416. Do not trust my math. Break out the old calculator. Blow the dust off of it for all of you guys who don't use it anymore. 3818 plus 230 plus 368. That is 4,416. That's what I've got. So at least this one's still working. And now, obviously that is less than the heat. So if you're in the 2017 code, guess what? When it comes to these non-coincident loads in the application, you're done with that. You can just take the heat. Obviously it's the larger. So when the AC is running, it's nowhere near 15,368 VA. So it's no big deal. So that's why you're using the heat. Now, if you were in 2017 code, when it comes to these, you're done for that. But if you're in the 2020 code, You're not done yet. Okay, so let's look at what you would do if it was a 2020 code. Now, I will remind you right here, here's a little tip. If you're dealing with a heat pump, I like to throw these little tips out to you. If you're dealing with a heat pump with a supplementary heat, it's not considered a non-coincident load. Add the compressor, full load current, to the maximum amount of heat that can be energized while the compressor is running, and remember to include all associated motors. So you take the heat at the value the maximum amount that the heat that can be produced while the compressor is energized, and take all those into consideration. Okay, and we will be talking about that in a little more detail when I do a coffee hour on the optional method, which I'll dig a little deeper into heat pumps for that type of scenario. So bookmark my site. Unless you're a hater, then move on. All right, so the difference here in the 2020 code, okay, is I already did the math. Everything stays the same. However, once I established, and remember this, for those that are studying the 2017 but are going to be testing on 2020, here's a significant change. If I determine that the AC is less than the heat, then the heat wins. But then in the 2020 code, I have to reevaluate the AC again if the AC compressor is, and it is considered a motor for our calculations, if that's the largest motor in the dwelling, then I have to recalculate it and take that air compressor at 125% plus all of the other loads that are associated with it, like the air handler and the condensing fan. So I'm going to redo that math. And I think most of us that are savvy would look at that and go, dude, it's still no way it's going to come up to beat 15,368 for the heat. So I'm not even going to worry about it. And you'd be right, but I need to make sure you know how to do it. So we're going to take that 3,818, which was for the air compressor, air conditioner compressor, and we'll do that at 125%. Then we're going to add the sum of the other loads, which is that the 368 for the air handler and that 230 for the condenser fan, which is 5,370.5. Yay. Whether you rounded this like we're going to do, that 0.5, we're going to go to 5,371. It's still not greater than the 15,368 VA for the heat with the air handler. So again, we just had to do it in the 2020. It makes you do that. And you still get to get rid of the AC. I'm still going with the heat. Heat is still the king. Whoop, whoop. So that's what I'm going to use in my calculation. All right. We do have a question in the live stream. That's why it pays for you to join me on the live stream. It says, quick question. Could you classify an AC as a continuous load for being on all the times more than 3? Absolutely not. That is not what we're going to consider as a continuous load. One, because the air conditioning unit cuts on and off in cycles, right? So it's not going to be typically on at its maximum output for 3 hours or more. So we would not calculate that as far as for our load calculation. That doesn't come into play as a continuous load. Good question, though. All right, so let's go to the next. So we know what to do, whether it's 2017 or we know what to do, whether it's 2020, when it comes to non-coincident loads. Okay, now, Now, here's the one step that people forget. Now that we're almost done, we're almost there, we have to take the largest motor and capture 25%. Now, people say to me, Paul, it doesn't say that in the code. My brain starts hurting. Well, I want you to go look at 220.50 real quick. Now, 220.50 does not say take the 25%. But what it does do is it gives you references to motors. It gives you references to things that you have to take at 125%. Well, theoretically, even though we applied a demand to that, we already captured the motor's value. So all this is trying to do is say, you know what? I'm not trying to get it again. I just need to get the 25% for that motor because I've already considered the motor in this calculation. I've already done that. But based on this, I need to capture that 25% because again, I would take a motor at 125. So I need to capture it. So it doesn't say it that way, but that's what it means. So don't let it hurt your brain. If you go look at the references that it makes in 220.50 and it also sends you to 440.6, you'll notice that it talks about 125%. We, at this point, haven't taken any of our motors at 125%, right? So all we're doing is trying to comply with 220.50 by trying to get that additional 25% so that we can theoretically take one of the motors that was the largest at 125%. Well, again, we're only trying to capture 25%, okay, at this stage, at this moment, okay? All right, and we're not doing it for all the motors, only the largest motor, okay? So, and here's another little thing that I'll tell you if you're in the 2020 code. If you're in the 2020 code and you happen to happen to be larger than the heat, and you already, remember when I said you compare them for non-coincident loads? If you use the air compressor at 125%, guess what? You've already done this step. You've already captured the largest motor and gotten that additional 25%. It's already done, so you don't have to do it again. So you get to skip this step. But if you're in the 2017 code, you obviously didn't do that, so you have to hunt for the largest motor. And remember, if we got rid of the AC versus heat, then we're not going to even consider the AC for this application. We're going to hunt for the next largest or the second largest motor in this dwelling. Okay, so let's kind of do this. So in our case, we'll say we did 2020 code, heat won, and AC was discounted. It was omitted. So now I got to go hunting for the second largest motor. Well, in my motors that are in my list that we had the in-sink waste disposal, we had the trash compactor, and we had the attic fan. Okay. So in this case, we already determined that the disposer was 1,127 VA. The trash compactor was 900 VA. The attic fans, which are motors, okay, somebody already did the conversion for us in our question. And again, we don't take all three motors. For this application, we're just taking the largest motor, and one of them was only 4.8 amps, so that was only 504. So the largest motor that we have in our case is the waste disposal, and that was 1,127 VA. Now remember, we're only trying to capture what? 25%. So we take the largest motor, multiply it by 25% or 0.25 if you're me and you like to break that mamma jamma down into actual decimals. Then that gives me 281.75.7. Remember, 220.5B says 0.5 and greater, round up. So I'm going to round up to 282. That is my contribution. Okay. Now, people want to know, well, why wouldn't I use the dishwasher and the 1200 VA for this? Because that is specifically an appliance, and it falls in the way that it's designed with its heat cycle and its motor and everything integrated. It has a nameplate that doesn't break it down into the same scenario where we would have the motor. Typical, a trash compactor will break down into horsepower, not always, but in our example it does. The attic fans are true motors, okay, that type of thing. Now, here's the thing I'm going to tell you for the real world, because I'm not doing exam prep today. In the real world, if you forget this 25%, it's not going to really change your calc. It's a small amount, right? We're only talking 282 VA. If I wanted to use the 1200 instead of the 1127, go for it. Trust me, it's not going to change your end answer. But when you're looking at your dwelling and you're looking for the largest motor should stand out. Whatever the largest motor is, okay, should stand out. So in our case, the largest motor in here is in-sink waste disposer. And we've captured that 25% right here. So what do? We add that to our math. So let's see here. We've kind of covered everything in this list, in this house, right? So let's kind of go through it. Remember, summary. The general lighting was 7,048. The fixed appliances was 6,929. The clothes dryer, again, was 5,500 VA. Again, we're applicable if you have a clothes dryer in your calc or in your dwelling. Cooking appliance, again, most of them have cooking, but if it didn't, you wouldn't add it. So if you're like doing an exam question that they don't give you cooking, then I don't assume anything. But anyway, that's 8,450. And then we compared heat versus AC, and in both the 2017 or the 2020 method, the heat was always going to be larger. Okay, so again, we took the heat, and of course, we captured that true largest motor, which was 282 VA. We add all these up again. Don't trust my math. Do it yourself. 7,048 plus 6,929 plus 5,500 plus 8,450 plus 15,368 plus 282. That is 29,000 in, wait a minute, something add up. Wait a minute, all these don't add up. I missed something. Sorry, let me do this again. 7,048. That's what I say, don't trust my math. Plus 6,929 plus 5,500 plus 8,450 plus 15,368 plus, oh yeah, I missed a step, 282. Yeah, 43,577. So we're good. Okay, I added all those up. Like all of these. Woo, everything we got. All of our steps. Okay. Now we could argue and say that's 1, 2, 3, 4, 5, 6 steps, but really there's little mini steps within each one. So in our Fast Tracks program, we actually give you a sheet that you use to work this up. And then really, you know, you can't use that sheet for your exam, right? And I always tell students, print those things out and laminate it, because you can get a dry erase pencil and you can actually use that and keep that in your code book as a bookmark. And when you go on a job and you want to calculate the service, real quick, use that and you can come up with a good idea. And you know what? You have some jurisdictions that require you to do a load calc for the dwelling. You could work it up on that sheet, take a picture of it, and send that to the inspector or send that to the jurisdiction, and that's your load calc. And say, boom, baby, I did a load calc for you. This is why I need this size service. All right, so we did this one. So now it's a 120, 240 volt service, single phase. So 43,577 divided by 240 gives us 181.57. Again, 0.5, we're going to round. So we have 182 amps. And again, due to that 0.5, that's how we round it up. So that's our size, 182 amps. Okay, so the next step we're going to do is, okay, I have 182 amps. I need to know what size overcurrent do I protect? Do I do that? Well, if you go to 240.6a and look, and we're going to do that, I'm going to do that. If you go and look, you'll see that, well, 175, it's not going to work for me because I have 182 amps. The next size up would be a 200 amp. So it's going to be a 200 amp circuit breaker in my case. All right, now, the next question that people ask me, so we size the overcurrent device. That is the rating of the service. The next thing that people will ask me all the time is they'll say, Paul, when can I apply 310.12? What tells me I can apply it? Well, you don't have to apply it, to be honest with you. You could go straight to 310.16 and size it based on terminal limitations, assuming no adjustment or corrections. You could go right to the ampacity table, and I could go to it. Let's do that. If I didn't want to if I didn't want to use the benefits of 310.12, let's say I didn't want to, okay? Because I know that there's a guy that works for a wire and cable company, and he gets a bonus every time you buy oversized wire or wire that's bigger than you need. And I know that he's got kids to feed, and you want to support him, not using any names of who it might be. Then I could go do that, and I could size my conductors based on without using this rule. And in that case, I could go with a, let's see here, I could go with a 3/0 copper. Perfectly fine if I want. Okay? Or, you know what? Yep, that's my load, so I have to go, so that's a 200 amp. Couldn't go to 2/0 because that's 175, so we need it based on a 200 amp. That's going to be able to handle the 182, so we're good to go. I'm good. Okay? And I'm okay with that. If you want to put 3/0 copper in there, I love you. You helped out whoever that fictional person was. Okay? I'm just saying. All right, now, but we want to use 310.12. And for you that are in the 2017 code, that's 310.15b7. And for you old timers, that used to be 310.15b6, right? Okay. All right, so let's do this. Get our hands dirty now, because we already know what the service rating is. It's 200. We already did that. All right, so for the service rated 100 through 400 amperes, and obviously ours was, it's 200, so right smack in the middle. The service conductor supplying the entire load associated with a one-family dwelling, or the service conductor supplying the entire load associated with individual dwelling units in a two-family or multifamily dwelling shall be permitted to have the ampacity not less than, again, not less than 83% of the service rating. And we've already established the service rating at 200 amperes, okay? So that's A. Now for B, 310.12b, this applies to feeders as well, okay? But again, it has to handle 100% of whatever the load is at the end of that feeder, okay? So in our case, again, we're going to keep it simple because I will do future coffee hours with optional and we'll do other little things. And I guess I should say now it's over an hour. So again, for you hung with me, I'm sorry, I'm long-winded anyway. We're almost there. Hang with me. All right. So in this case right now, we know the rating is 200 amperes and we're doing a service. So we're going to be applying 310.12a for our application. So multiply the minimum size service or feeder rating, which in our case is 200 amps, which is 200 by 83%, which is 166 amps. So let me do this. So it'd be 200 times 0.83 is 166, which is, then I have to select a conductor that's under the 75 degrees C column, okay, because it is over 100 amps, right? And we're in 75 degrees C. 110.14 C gives us all those rules. So I'm going to select the conductor for that. I have to have one that's at least what? 166 amps. Can't be less than that. So now we're going to go back to 310.16 if you're in the 2020 code. And I haven't showed you to go to that table yet because I like to teach you. I don't want you to cheat and go to some little table. Who needs the table? We don't need the table. We know how to do the math. So we're going to go here under 75 degrees C, and we're going to be looking for conductor. So it looks to me that I can have a 2-aught, which is smaller than 3-aught, obviously. So, you know, there you go. It could be a 2-aught. So I can select that. Now, that is the minimum size. It cannot have an ampacity less than 83% of whatever the service rating is. So even if I have some adjustment and corrections that have to take place, like ambient temperatures, because that's usually the one that you might have to use, you typically not going to be more than this case, not more than 3 current carrying conductors, but you might have an ambient issue. I'm going to do the adjustment and corrections the same as I normally would, but remember that ultimately my conductor sizing using 310.12 cannot be less than 83%. So all I'm going to do is go through the math and do an adjustment and correction. At the end of the day, I still have to remember I cannot be less than 83%, right? Okay. So, okay. Elwood, we said that. You need to rewind and listen to it. I said that, bruh. All right. So let's go back to it here. So in our case right here, it's 2-aught copper. Let's state otherwise. I'm a copper guy, so we're going to run copper. Can run aluminum, perfect fine. So the minimum conductor size per 310.12a would be a 2-aught. Now, it's 4-aught aluminum would be the equivalent. Now, if you want to cheat and look at the table, go on and look at the table, which is 310.12. It says beside it, it has an N. Now, this was previously, back in Informative Annex D, the table. Now, back earlier than that, like the 2014, it was actually, I believe it's 2014, was actually in the code. It got removed in 2017, got moved to the back. Well, people had a fit. And so I guess the power of the people, maybe we say the power of the people, it moved it from there and it ended up being placed back in 310.12. Okay. One thing to remember about this table, let me give you some tips. You cannot use this table, okay, if there's an adjustment and correction involved. You got to do the math like we just did. Still can't be less than 83%, but you can do an adjustment and correction just like you would normally, as long as the end value is not less than 83% of the service rating, okay? If there is no adjustment, if there is no correction, right? Then in this case, if there is no adjustment, there is no correction, then I can pull straight from this table, right? And do the applications, okay? That's the way to do it. One thing to remember, when you're doing feeders, In the feeder application, if you look at the code, it says it'll tell you which ones apply. If you're doing a feeder application, then you're only going to apply what? All these rules. You got the whole thing is 310.12a through D is going to apply. But if you're doing a one family dwelling or individual dwelling units, and you're utilizing 2 ungrounded conductors and a grounded conductor neutral and a 208Y120, then you're only going to apply 310.12a through C. You're not going to deal with D, which is the grounded conductors. So in other words, it can't be reduced, right? It's got to be full sized, okay? So in that scenario. Now, when it comes to sizing the grounded conductor, D tells us that the grounded conductor shall be permitted to be sized smaller than the ungrounded conductors. That's true. So if I buy an SE cable, typically the grounded conductor is going to be smaller anyway. Now, I'm going to tell you a little tip. When it comes to like SE cables, the grounded conductor typically is going to be 2 sizes smaller than the ungrounded, okay? Already figured in. So if it's a 4/0 aluminum, then the grounded conductor is going to be no smaller than a 2/0 aluminum, okay? Because there's a 3/0 in there and it's 2 sizes smaller. That's in our standard UL 854 when it comes to SE cables. But this rule tells you it can be smaller, but it doesn't circumvent the fact that you, guess what? You still have to do a load calculation, right? Now, it never has to be larger generally than your ungrounded conductors, right? But in this case right here, you're going to have to do a load calc. And so that's why you need to know it, because it tells you the requirements of 220.61 and 230.42 for service conductors, and the requirements of 215.2 and 220.61 for feeder conductors are met. So you got to follow the rules. And you have to look at the load, and you got to be able to handle the maximum unbalanced load, okay? After that, that's kind of going to dictate to you your sizing, okay? But this rule does permit your grounded conductor to be smaller, provided you do the calculations, okay? I think most people will go with the standard SC they buy. Most people, if they're running individual conductors, then they're probably going to so that they don't have to get into the calculation, they're probably just going to run them all the same size. The ungrounded and the grounded, all the same. I think that's probably their way of doing it so they don't have to calculate the neutral. I mean, we're still going to do that, right? But I just kind of want to, right now we're sizing ungrounded conductors. All right, so there we go. So again, for the 200 amp, minimum size conductors would be a 2/0 copper or 4/0 aluminum. Okay. Bonus question, what is the minimum size for the grounding electrode conductor to the water pipe ground electrode, assuming that it is supplemented? Okay, so we'll assume that it's supplemented and everything's good. So we're going to say, what would you be required for a water pipe ground here? Okay, so in this case, if we're going to do that, it's all based on the conductor sizing. So in this case, our conductors were what? A 2/0 copper. So I'm going to be going to where? Where would I go? 250.66, right? So let's do that. Let's do it. Might as well do it while we're here. Let's finish this bad boy out. 250.66, grounding electrode conductor. That's what we're being asked. We're going to go down to the left side. We'll assume copper. And in this case, it was 2/0. So between 2/0 and 3/0, or 2/0 or 3/0, it looks like it's a 4. So it is indeed a 4 gauge. And I think that's what you're asking, Adam. So that 4 gauge would be what we would run to that water pipe ground. Now, if you were lucky enough to attend my Grounding and Bonding 12-hour webinar series, you would have learned all of the nuances for sizing grounding electrode conductors to the different types of electrodes. Did you make it? Did you miss it? Do you want to watch it again? Well, guess what? You got to be a monthly subscriber or an annual subscriber over on our website, because that's going to be posted on the private members area in the next couple days. 12 hours of grounding and bonding. Doesn't that get you excited? You know what gets me excited? Watch. Woo! I'm excited. You should be too. All right, so let's kind of go on to the next thing. All right, so let's kind of see how this would apply in our scenario so we can cover all those little pieces. All right, and you're right, Adam. I need some more coffee for that. Everybody thinks I'm a stuffy educator. When I go on tour and I'm teaching in venues, I'm always shirt and tie, but you get to see the real Paul on these streams, okay? Just saying. All right, not the all business, Paul. All right, so here's an example. We got service coming in right here. All these are service entrance conductors coming through. Boom, 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 going to the line side. Everything's good. All right. So in this scenario right here, these conductors right here, these service conductors, are seeing 100% of the load, okay? Everything on this panel is being seen, 100% of the load, okay? So sizing these conductors all the way up to the point of attachment, okay? Again, since I'm handling 100% of the load here, then I can apply it perfectly. I'm able to apply this rule. So this 200 amps times 0.83 is 166 amps. Again, I size these conductors accordingly, okay? And they were good to go. Now this scenario right here is the same type of scenario. So this is a feeder because here's our certain. Now maybe this is an example of using 230.85. Maybe this is an example where this is a service equipment and this is outside, right? Now, of course, I probably wouldn't need this main breaker here because this would be my service equipment here. Okay, but sometimes you buy panels, it's cheaper to buy it with the breaker than it is to buy main lug only. I'm just saying. Sometimes it's cheaper. So anyway, I'm frugal, so I bought the one with the breaker, and or they gave it to me for free. Wink, wink. Square D, Schneider, Eaton, looking for a sponsor. All right, so no, I probably wouldn't sell out. All right, so here's my service coming in. It's coming through. Now, here's another example, is that these feeders are seeing 100% of the load, okay? And so, again, I would be able to apply the 83% to sizing these feeders, okay? So I can apply that to all of this. This whole set here is seeing 100% of the load. And so the reason I throw this one in here is because, people are impacted by the new rule for the emergency disconnect outside. And we cover that in a podcast. So make sure you also go listen to my podcasts. They are pretty informative, if I say so myself. And we do have a new one that launched today. So make sure you go listen to that. And I'm talking about what other than 310.15b7 or 310.12 on today's episode. So go check that out. All right. So here's where we applied that. And again, because of that, that means these only had to be a 2-aught copper or 4-aught aluminum, depending on whatever you wish, okay? But this is your service disconnect means, and it can serve as the emergency disconnect requirement as well in the 230.85 rule. All right, so now we've done all that. We sized our conductors, and now we're like, okay, Paul, I got you, but we're doing a standard method. And remember now, this is what we have to use to size the neutral, even if we did an optional method. Same variables. But now we're sizing what? The neutral. Okay, so first thing I will tell you is that at a quick glance, and we don't count them all because some of them we've already done and we've already wrote them down, like the dryer and the cooking. So we'll cover those in a second. But for the neutral loads that stand out to me and you, that square footage value, 3VA, that's all has a neutral load associated with it, right? The two small appliances, in our case, there was 4 of them. All of those are 120 volts, so they all have a neutral contribution. The laundry, it's a 120 volt neutral contribution. The water heater is not, it's 240, not a contribution. The dishwasher, in-sink waste disposal, the trash compactor, and all of those attic fans, they're all 120 or 115 for this disposal. All of them have a neutral contribution. So we're counting those. Clothes dryer, we're going to do those at 70%. We already have that written down, but we'll cover that. The cooking, the same thing. We take that at 70%. That's what it told us to do in 220.61b, right? The electric heat, nah, that's 240. Ignore it. We've got the air handler, which is 115. The air conditioning compressor, that was 230. No neutral contribution there, so we don't consider it. And of course, we have the condensing fan motor. That is 115. We do have to take that in consideration, okay? All right. Now, here's the easy part about this. You've really already done the work for most all of these. You just go back and look at what your values were for your standard method for most part. So in this case, we had 7,048 for our general lighting and all of our small appliances and laundries. Remember, they're all neutral loads, so that value, you write that down, 100%, it counts, okay? Next, our appliances. What applies and what doesn't apply? Well, you notice we took off the water heater, but all of the other ones are very much applicable. Now, I'm going to see if I can trick you here. Let's see. So I'm taking the dishwasher. We already did that VA. We're taking the in waste disposal. We already have that VA from earlier. The trash compactor, we already have that VA. We did it earlier. The 3 attic fans, we already did that. We had that earlier. So we're going to add all of these up together. 1,200, 1,127, 900, and 1,512. That's 4,739. Don't trust me. Remember, many people say I'm not a trusted resource. So go do it yourself. 900 plus 1,512. That is 4,739. So that is right. Calculator did work this time. Now, how many appliances do we have? 4, right? Wrong. We have 3, 4, 5, 6. So we definitely have 4 or more. Okay? Little math test for you there. So we have 6 of them. So we definitely can apply the 75%. So that's a question that many people ask. They say, well, why am I applying the 75% to it? Didn't I do that because we were doing the ungrounded conductor? What's good for the goose is good for the gander. If I'm doing a neutral, I can use the same allowances here, right? So I can apply the 75%. Absolutely. Keep it simple. Don't make it complicated. So in this case, only thing I'm dropping from our previous calc is the water heater. Okay. So I take that 4,739. I multiply that by 75% or convert to decimal 0.75. And that should be times 0.75. That should be 3,554.25. I'm going to drop the 0.25. Why? Because 220.5b tells me I can. And because I can, I is. So I'm dropping that down to 3,554. Okay. So that's my calculation values for my appliances. Next, we got that clothes dryer. All right, we're going to cover both on this one. So that clothes dryer, remember what we did earlier? We already wrote this down. We took the 5,500. Remember, the allowance in 220.61b says we can do what's another demand value. We can demand it even more. We can reduce it even more. So we get to take that value and do it at 70%. And of course, y'all know I love breaking down to decimal. So that's 0.70. So 5,500 times 0.70 is 3,850. Write that down. That's your neutral value. You should have wrote that down earlier when we first started, but write it down again. Now let's deal with those counter-mounted cooking units, right? Now we already did that math and we ended up with 8,450 VA. We already did it. But guess what? We get to take an additional 70% reduction. So what we do is take 8,450 VA times 70% or 0.70, and that drops it to 5,915. Now I'm going to double check that because you always should. 8,450 times 0.70, 5,915. Yep, check. We're good. So write that down. That's your contribution for the neutral for your cooking. Next, we got to take care of that AC. Okay, we didn't have any heat, but we had the AC, which at any given time, since we're not talking about AC versus heat here, they do at any point, you're going to have neutral contribution. Okay, and since there is no heat, we still have to capture the neutral loads that will be present there. Okay, unlike with the ungrounded conductor sizing, we captured the heat because it's larger than AC, so it didn't matter. It was larger, the AC is not a factor. Here, I still have to capture those neutrals, that load for neutral. So we had that air handler and we had the condensing fan. Again, we take those values that we calculated earlier. 3.2 amperes times 150 volts. That's how we get VA, by the way. Basic math, okay? So here we've got 230 for the condenser fan and we've got 368 for the air handler. Add those two together, 598 VA. Just add that to your list. That's your contribution. Now, lastly, we still have to get that largest motor again. So we have to look for that largest motor, okay? So let's look at those values for the largest motor in the neutral contribution. Well, we can go back and look, and again, probably more often than not, it's going to be the same motor that you used in the original standard calculation for the ungrounded conductors or hot conductors. So in this case, it's still the in-sink waste disposal. So again, you might take the exact same value. It's 1127 VA times 0.25. It is 281.72. Again, 0.72. Because of 220.5B, we're going to round it up to 282. So that's our contribution. So we covered all the neutral loads. So let's add them up. 7,048, 3,554, 3,850, 5,915. The two motors for the air conditioning, we had 598. And then that contribution for the motor, 200, the largest motor was 282. Again, that's just that 25%. Let's add them all up. So I'm going to go 7,048 plus 3,554 plus 3,850 plus 5,915 plus 598 plus 282. That equals 21,247 in our values. Okay. So we're going to take that value and we're going to divide that by 240 volts. Okay. In this case, it would be 88.52.5, round up. That is 89 amperes due to the rounding allowance. Okay. If you didn't want to round, you don't have to. You can take full value if you wish. But at this point, it's 89 amperes. So what are we going to do? Then we're going to have to go and find a conductor. And remember what it said? We could have a conductor, a grounded conductor that can be smaller as long as it can handle the calculated load. And we did that, the maximum imbalance load. We already done. We just did it. We just calculated it out. So in our case, we go to 310-15B16, or if you're in the 2020, 310-16. At some point, I don't need to say B16 anymore, but I know we got some folks that are still on the 2017, and we got some states that are still on the 2014, believe it or not. How's that blow your mind? It's still on that. So I'm going to go to 310-16 because I'm working out of the 2020. And I'm going to go down and I'm going to look and see what I've got. Now, in our case, remember something. Since our values are, we got to adhere to 110.14C, and we're under 100, you typically would say, well, I'm going to have to go to the 60-degree column. All right, so I'm going to tell you that most times in these cable assemblies, what you're using is THHN, THWN-2, and the terminals are going to be rated 75 degrees C. So you're going to use the 75 degree C value. Okay. On an exam, just be careful in your calculation and make sure you validate all of that information. Okay. But I'm going to tell you right now that we're using THHN, THWN-2 for our application. So I'm just giving you that information. And so we need to go into the 75 degree column, and we're going to go down and we need one that's going to handle our 89 amps. Well, it looks like to me I need a 3 copper, or I could get that in aluminum. I'm going to need at least a number 2 for that to be able to handle the 89 amps. And that's going to be sizing my grounded conductor. Okay. All right. That's pretty much it in our calculation. So, really have nothing. It's just that simple to size everything through the calculation. So it doesn't get any more complicated than that. So I will go back to my main screen, and there's absolutely nothing here. So I thought I was here, so I'll get rid of that and just go back to the live screen. I guess I don't have it set up. So that's all we have for the calculation. I went a little longer than normal for my coffee talk or my coffee hour this morning, but my sincere hope is that you got something out of today's episode. And I know it looks awful pale because I didn't change the camera's color depth and I only got one studio light on today. So again, bear with me. I'm feeling a bit blue, but hopefully you got something out of this episode and you've enjoyed it. So folks, that's actually it. And hopefully you enjoyed it, and we'll see you on the next coffee hour with Paul Abernathy. Till then, stay safe. God bless. You've been listening to Electrify with your hosts Paul Abernathy and Jay the Basement King Grunberg.